Assalamualaikum everyone. So today we're going to continue on the topic of thin film deposition. So if we look back to the previous lecture, there are four process of thin film, PVD, CVD, which we already covered in the previous class. So next will be doping and oxidation. Let us look into doping process first. Doping means we introduce impurities into the semiconductor crystal so that we can modify the conductivity. Two of the most important materials silicon can be doped are boron with 3 valence electron and phosphorus with 5 valence electron. And other material that can also be used are aluminium and indium with 3 valence and arsenic and antimony with 5 valence. Now let us recall what is valence electron. If you can remember from material engineering class, valence electron is supposed to be an electron that available to be lost, gained or shared in the formation of chemical compound. It is located at the outer layer of the atom. Okay, so the outer orbit of the atom. So if you can see here for boron, we have 3 electron, 3 valence electron. Silicon we have 4, and then antimony we have 5 valence electron. In the doping process, the dopant will be integrated into the lattice structure of the semiconductor crystal. So the number of outer electron will define the type of the doping. For example, the dopant with 3 valence electron will be used for p-type doping and 5 valence electron for n doping. There are 2 types of doping in semiconductor. One is n-type, which is negative type, or we call it as donor. So in this process, the silicon crystal will have extra electron after the doping process with the n-type dopant. So the n-type dopant are phosphorus, arsenic, antimony, where they have 5 valence electron. As for p-type or positive type, and we call it as acceptor. When the doping process happen, the silicon crystal will have extra hole instead of extra electrons. So the p-type doping material is boron, aluminium, nitrogen with 3 valence electron. So here are the n-type and also p-type donor. So if you can see here for the n-type, after the dopant incorporated with the silicon, there'll be 1 free electron contributed by the donor. And so for p-type, there'll be 1 hole. This is acceptor impurity creates the donor will create the hole. Okay, so after the incorporation, there will be 1 hole over here. For n doping, for negative doping, so the 5 valent dopant has outer electron more than the silicon atom. So silicon atom have 4 outer layer for the electron valence, right? So but for the donor, they have 5. So after pairing with the silicon atom, there will be 1 electron that are free, that cannot be paired with the silicon. Okay, so after that, there's 4 outer electron combined with every one of silicon, with the 5th electron is free to move and serve as charge carrier. So this free electron will be the charge carrier in the for the electrics. Okay, so this free electron require much less energy to lift it from the valence band into the conduction band that the electron, which cause the intrinsic conductivity of the silicon. So the energy for this free electron is much less energy is required to lift this one from the valence band. Okay, so that's why it can be used as the carrier of the electric. So the dopant which emit an electron is known as the electron donor. So meaning that it will create one free electron that it donate the electron to the silicon, so that electric charges can be moved via this electron. For p-doping, the trivalent dopant can catch an additional outer electron, so leaving a hole in the valence band of the silicon atom. So for example, this one, they have 3 only, right? So once it's paired with the silicon, okay, so there'll be one free hole over here. So therefore, the electron in the valence band become mobile. So this hole will give possibility for other electron to come in and then move to another one. So this hole create a like a place where the electron can move from one to another. Okay, so the hole move in the opposite direction to the movement of the electron. Okay, so the necessary energy to lift an electron into the energy level of indium as a dopant is only 1% of energy which is needed to raise a valent electron of silicon into the conduction band. So meaning that less energy is needed in order to move this the electron into this hole from another to one, instead of moving the other valent electron. Okay, now let us see the band gap in the semiconductor and compare it with the insulator and the conductor. So first, let us see the insulator. For insulator, the band gap energy between the conduction band and also the valence band is very high, so which is impossible for the electric conduction. So as for the electron, there is no band gap between the conduction band and also the valence band. That's why the electric will move freely. As for the semiconductor, we know that semiconductor is not a good electric conductor, but it can conduct the electric. By adding the dopant, it will improve the conductivity of the electric by using the positive and negative band over here. Okay, the positive and negative ion. Okay, there are two types of dopant process that can be used. One is diffusion and another one is ion implantation. Now let us look into the diffusion process. So for the diffusion process, dopant can be introduced to the substrate surface in the form of the deposit film, or substrate can be also placed in the vapor containing the dopant source. Okay, so this process usually performed under 800 degrees Celsius to 1200 degrees Celsius of temperature. So usually it is operated in a very high temperature. Okay, so dopant movement within the substrate is strictly a function of temperature, time, and the diffusion coefficient. Okay, so it also depend on the type and quality of the substrate material. But because of the nature of the diffusion, the dopant concentration usually concentrated on the surface here. Okay, so on the face here, when it goes down, it become thinner, so less, meaning less ion is being implanted inside here. Okay, so due to that, to obtain a uniform concentration within the substrate, the wafer will be heated further, so that it can drive all the dopant on the surface into the Si substrate. Okay, so as I mentioned previously, the diffusion will occur usually at a high temperature. Although the diffusion process is not expensive, it is highly isotropic. The next process is ion implantation. So ion implantation is the most widely used method for the silicon doping. So in this process, high energy ion beam implanted charges dopant inside the semiconductor material as projectile, and then it also able to implant any ion at various depth of the substrate compared to the diffusion. Ion implantation is much more extensive process, require special equipment compared to the diffusion. So implantation is accomplished by accelerating the ion through a high voltage field as much as 1 million electron volt, and then by choosing the desired dopant by means of a mass separator. In a manner similar to that of a cathode ray tubes, the beam is swept across the wafer by set of deflection plate, then ensuring uniform coverage of the substrate. So the complete implantation operation must be performed in vacuum, so that the concentration of the ion implantation will be better. So the high velocity impact of ion on the silicon surface will damage the lattice structure and result in lower electron mobility. So this condition is undesirable, of course, but the damage can be repaired by the annealing step, which this annealing step will involve heating the substrate to relatively low temperature, usually around 400 to 800 degrees Celsius, for around 15 to 30 minutes. So annealing provides the energy that silicon lattice need to rearrange and amend itself. And another important function of annealing is it will drive the implanted dopant, and implantation alone embed the dopant less than half a micron below the silicon surface. So annealing enables the dopant to diffuse to a more desirable depth of a few micron. There's some problem with the ion implantation. The common problem will be in ion implantation is channeling, where the high velocity ion will travel deep into the material via channel along the crystallographic plane before it finally being stopped. So in this part, I would like to ask you to look into this problem. How does the try to find what will be the solution for channeling. So here are some video to the doping and also ion implantation process. As for diffusion, I am not able to find a good video for you to refer to. So I hope you can get new information from this video. So now let us move to the oxidation process. Oxidation process is a process where oxide layer is grows on the surface of the substrate. Okay, so this one is resulting from the reaction of the oxygen with the substrate material. So oxide film can be formed by using deposition techniques. For example, thermally grown oxide will display a high level of purity than the deposited oxide, so because they are grown directly from the high quality substrate. However, deposition method must be used if the composition of the desired film is different from the substrate material. So there are two methods that we can use. One is thermally grown the oxide, but another one is via deposited oxide. Thermal oxidation is one of the process to perform the oxidation on silicon wafer. Usually, the silicon wafer will be oxidized in the furnace for at temperature around 1000 degrees Celsius. So the furnace will consist the quartz tubing, so here, and then the wafer will be placed in the carrier here. So then, in order to avoid the crack or warping, the quartz tube is heated slowly, which around 10 degrees Celsius per minute. So the temperature is increased at that rate, and then the tempering of the tube can be done by a very accurate via individual heating zone. Okay, so because there are several heating zone in the quartz tubing. So the oxygen will be supplied into the tube. Okay, so once the oxygen is supplied inside here, at the wafer surface, it will create silicon dioxide. So a film of glass with amorphous structure will be formed on the wafer. So depending on the gases that supply into the tube, different oxidation will occur. So a thermal oxidation has to take place on a bare silicon surface. So for this operation, it has to be bare silicon. So the thermal oxidation can be divided into two types, which is dry and also wet oxidation. So this picture shows the growth of silicon dioxide on top of the silicon. So in the initially the wafer will be put under the oxygen atmosphere, and then the oxygen will react with the silicon to form the silicon dioxide, and finally almost 50% of the dioxide growth into the substrate. So in order to know the segregation coefficient, here we can use the calculation K, coefficient of segregation, equal to solubility of the dopant in silicon, and also divide by the solubility of dopant in the silicon dioxide. So if the K value is greater than 1, therefore dopant accumulate at the surface of the substrate. So it's on the surface of the substrate. If the K is less than 1, meaning the dopant is accumulated in the silicon dioxide. So for the dry oxidation process, the oxidation will take place under the pure oxygen atmosphere. So the silicon and oxide will react to form the silicon dioxide as shown in the equation below. Si plus O2 equal to SiO2. So this process usually perform at temperature of around 1000 to 1200 degrees Celsius. So in order to create a very thin and stable oxide, the process can also be done at even lower temperature, which is around 800 degrees Celsius. Some characteristic of dry oxidation are it is a slow growth of the oxide, and it has high density and high breakdown voltage. So for wet oxidation, on the other place, the oxygen is led through a bubbler vessel filled with heated water, which is around 95 degrees Celsius, so that the addition of water in the present in the quartz tube is in terms of steam. Okay, so then the oxidation in the quartz tube will become Si plus 2H2O, meaning that it is not purely oxygen anymore. It become steam of water, so that it become SiO2 plus 2H2. So this process is usually performed at a temperature around 900 to 1000 degrees Celsius. The next process for oxidation is via vapor deposition. Previously, it is purely the silicon material, but if the silicon surface is covered by other film, the oxide layer has to be created in deposition process, since thermal oxidation need bare silicon surface to be oxidized. So in deposition process, oxygen and silicon are added in gaseous state. So there are two processes that can be used for the vapor deposition process. The first process is silane pyrolysis. So pyrolysis means a cleavage of chemical compound. In this case, the gas silane, which is SiH4, and highly purified oxygen, O2. So since the toxic silane tend to self-ignite at ambient air when it is above a concentration of 3%, therefore it has to be diluted with nitrogen or argon below 2%. So at about 400 degrees Celsius, silane will react with the oxygen, then it will form silicon dioxide, and hydrogen will be released. So SiH4 plus A2 O2, so it will become SiO2 plus 2H2. So the quality of the dioxide is quite low. So as an alternative, a high frequency stimulation at 300 degrees Celsius can be used, so it can stabilize the oxide generate on the surface. The next process is TiO deposition. So the liquid TiO, which is SiO4C8H20, which used in this process, contain the required element, which is what we want, which is silicon and oxygen. So under a vacuum condition, the liquid will be transformed into gas and is let into the tempered quartz tube with the wafer at around 750 degrees Celsius, and then SiO4 CH4 will create the SiO2 and byproduct. So byproduct is here is in term of H2O, in term of in gaseous state, will be produced. So the uniformity of this oxide layer depend on the pressure and the process temperature. So the film created using this process is has high electric strength, and it is very pure. In semiconductor industry, oxide is used for multiple reasons. For example, as isolation, where it become the interlayer dielectric. It can also use as scatter oxide is in the ion implantation, and then use as adaptation layer for low cost technology, planarization for edge rounding, mask layer, and then alignment mark, and also cover layer. Now let us look at one example. So during a processing sequence, 3 silicon dioxide layers are grown by oxidation to 2000, 3000 and 1000 respectively. So how much of silicon substrate is consumed? Assume the ratio of oxide to the amount of silicon is 1 to the 0.44. Okay, so how do you want to solve this equation, this problem? So the answer is, first, the total oxide thickness will be, the first one will be 2000, 3000, and then the third one is 1000. So what you have to do is just sum up all the value, so it becomes 6000, right? So 6000 of atom. The ratio of the oxide to the amount of silicon consumed is found to be 1 to the 0.44, right? So therefore, to grow 6000 atom of oxide, approximately it is like 0.44 times the 6000 atom. So then it's equal to 2640 atom layer of silicon substrate will be consumed. So that's the end of the class. Thank you for listening. So see you in the next class. Assalamualaikum.